Okay, that's my job.
You seriously have no secrets? You have no secrets?
Oh, I've got a lot of secrets.
Stays the same.
Okay.
That's what makes them secrets.
So you can get rid of a few. Like you still have on your chest. We're very talented.
Okay. So I gave you the lecture notes on these rate determining steps. So here's the leap of faith that you need to take on this lecture. You all are used to reactions taking place in one simple step, like hydrogen reacts with oxygen to produce water. Okay? This is what we refer to as an elementary step. So if a reaction takes place in just one step, the only thing that determines the rate is going to be either the concentration of the hydrogen, the concentration of the oxygen. That's it, okay? But once you get into more and more complex reactions, you'll see that a lot of reactions just don't happen in one step. Like, for example, the lab that you're going to do next week, one of the things we're going to look at is the concentration of the acid, hydrochloric acid. And what's going to be weird, and this will make sense next week, is that the overall reaction has hydronium ions as a product. So you wouldn't think the concentration of hydronium ions would impact the reaction because of the fact that hydronium ions show up as a product. It's like, well, if you're making hydronium ions, how could the concentration of the hydronium ions alter anything if it shows up as a product? Okay, that doesn't make any sense. So, well, when we run into that, we have to figure out, okay, there has to be something going on. So if you've ever seen like the Wizard of Oz, okay, and you've got the wizard behind the curtain. So what that means is that when you get into these complex reactions, there might be something going on behind the scenes. Like there's a wizard behind the scenes pulling the levers.
Defying gravity.
Defying gravity. Yes, there you go. Okay? So let's start with this analogy. Imagine that you have 3 different funnels. Okay? You've got like a medium-sized funnel, a very small, narrow funnel, and then you've got this big, massive funnel. Okay? And I'm going to pour water into, and these are like stacked vertically, okay, where the water can flow through like this, right? So which of those 3 is going to determine how much water we get out the bottom? Smallest one, right? Because you can pour all the water that you want into this one, okay? But as that comes into here, there's only so much water that can come out here. So if you can't overflow it, then you just can't fill that one up above to the point of overflowing, because you can't. So you can only put into the top one how much water you can get out of the second one. So what determines the rate of any reaction is the slowest step. Okay? So your mantra is you can't go faster than the slowest step. Okay? Does that make sense? So it's somewhat analogous to, all right, hey, we're going to try and get everybody out of the school. Okay? It's a fire drill. We need to get everybody out of the school. Well, one option is we just knock down an entire wall of the school. Cool. Right? Nice. Everybody can get out very, very quickly. It's cool. Unfortunately, we knocked down the wall. Small problem. Now, in contrast to that, Satan's like, whatever.
Build another one.
Insurrectionist. Whew, okay. So, the other side of that is that, no. All the doors are blocked except for one. And we've got to get everybody through one door. It's like, man. Okay, that's going to take forever because that's going to be the slowest step. So you kind of have a visual. Okay? Now, on that sheet that I gave you, this is all about the terminology. Okay, so let's just begin to go through that. So if you look at, so when you look at this in terms of molecularity, okay, molecularity is just, I always thought was a fun word to say, like, oh, molecularity. So you're going to have, molecularity just refers to how many molecules or atoms have to collide to make a reaction happen. So unimolecular is just, that's just like, for example, hydrogen peroxide would decompose into oxygen and water, okay? Magnesium carbonate would decompose into magnesium oxide and carbon dioxide. There's nothing that really has to collide. It's just one thing, okay? Now, bimolecular. So there's a couple of things that you need to understand about this. Water, for example, would be an example of something that's bimolecular because of the fact that you have to have hydrogen and oxygen that are combined. So you have two things that have to combine. Now, that can also happen if you want to make oxygen. So if you want to make oxygen, you'd have to have two oxygen atoms combined to make O2. So don't look at this and go, oh, that's just unimolecular because of the fact that it's just oxygen. This is still bimolecular because of the fact that the two oxygen atoms have to combine to make O2. So just because something is bimolecular doesn't mean that there has to be two different types of atoms. What it means is that two atoms have to combine. They might be different, they might be the same. Okay, so the easiest way to remember this is like a bicycle. Hey, bicycle has two wheels. Bimolecular means two things have to collide. Might be the same. One might be a square wheel, one might be a round wheel, or they might be two round wheels. But that's what that's going to look like. Now, termolecular is pretty rare because termolecular means that you have like 3 or 4 different things that have to combine. So the reason that that doesn't happen very often is just because of like orientation. So the molecules or the atoms would have to combine and collide just in the right orientation, like a key in a lock. And they would have to combine in just the right random collisions for the reaction to take place. So termolecular happens, but statistically that's tough because everything would have to collide just right. So that's just terminology. It's like unicycle, oh, that's one wheel. Bicycle, that has 2 wheels. You go from there. Okay, so let me kind of go through and explain what this looks like. But first, hold on. I got to get one thing using the demo. Hold on. This will make some clear.
Is that one of the things, is it one of the pets?
Huh?
Where you press the button and they open?
No.
Do you know what I'm talking about?
Oh,
It's
like,
like-
from the McDonald's toys?
Yeah, they like roll up into a ball.
Oh my gosh.
Like a cookie?
I think
what it looks like.
That's
Yes.
not.
Boom.
I do.
Okay.
And there's little animals.
Let me do some writing here, okay?
I thought this was really
Sure.
cute.
Wait, geopens?
No.
I
I had
know.
rods.
Sign in your drink. Stay Gersh strong.
No.
Wordplay is that.
Do not start this.
I hope your nose gets better. Hope they take a little
He comes in, he just he looks like Voldemort, it's just all really good. It's just flat.
It's just too little.
Like a negative photo of Voldemort.
Imagine imagine going up and going like that.
You said it is.
You have to. You can either go for the eyes or the nose.
Stop talking.
Talk about.
Okay, so let me give you a simple example.
That doesn't look very simple.
Just say
So let's say that we know this reaction takes place. Nitrogen dioxide reacts with carbon monoxide to produce nitrogen monoxide and carbon dioxide. Okay? Fairly simple reaction. Now, here's where what you think is going to happen doesn't match with what actually happens. So if you were to look at this NO2 plus CO2, if that was what we call an elementary reaction, and that's the only thing that happened, was NO2 reacting with carbon monoxide, you would think, just based upon that reaction, that it would be based upon the concentration of carbon monoxide, and it would be based upon the concentration of carbon dioxide, and you would think, if this was an elementary step, and this is a huge if this reaction took place in just one step, you would look at this and go, oh, R is going to equal K times the concentration of NO2 times the concentration of CO. You would think it would be a second order reaction overall, first order with reaction with respect to each of those. Okay, if it was one simple reaction, this is what you would think would happen. Okay? Now, you actually run the experiment. And in the experiment, you realize that it's actually second order with respect to NO2, okay, the nitrogen dioxide. The carbon monoxide doesn't have anything to do with it. It's like, well, that doesn't make any sense. So then it becomes like a spy novel, like who done it? How do you explain the fact that a rate is based upon the concentration of NO2, which makes sense, but what doesn't make any sense is why it would be a second order reaction with respect to the NO2 when in reality the coefficient in front of the NO2 is just a 1. So it's like, at this point it turns into a Wizard of Oz story. It's like, okay, who's the wizard behind the curtain? Who's pulling the levers to make this appear differently than what we think it should? So this is where you propose different mechanisms. So one mechanism is that what we're going to say is it might work, it might not. So what we're going to say is that one possible idea is that NO2 can react with NO2 to form nitrogen trioxide and nitrogen monoxide. Okay? Then, and that would be a slow step. So in other words, what we're saying is that why this would fit is because of the fact that if this is a slow step and NO2 is combining with NO2, that would make sense with why the rate is a function and a second order with respect to the NO2. Cool, that fits. But that doesn't fit with the overall reaction. It's like, this is bad, okay? What's going on with the wizard behind the curtain? Now, the other part of this is what we call an intermediate. So what you would form here in a slow step is that you would make this nitrogen trioxide, okay? Now, what's important here is that this is going to be a slow step, okay? We're going to make this, it's going to be a slow step. But the next step is the NO3. It can react with carbon monoxide to make NO2 and carbon dioxide. So here's what would happen. If this is your slow step, as soon as you make the NO3 is going to get consumed in the next fast step. So this is why this reaction can't take place any faster than the rate at which I produce NO3. Because as soon as the NO3 is produced, it gets consumed. So here's somewhat of an analogy. Let's say it's the weekend and you're much younger than you are now. Let's say you're in grade school and you love chocolate chip cookies. Okay?
Yeah.
Right? So like you live for your mom's chocolate chip cookies.
Still do.
Okay, good.
Oh, weird.
So the slow step with Cohen would be the production of the chocolate chip cookies. So you can't consume the cookies any faster than your mom makes them. So the slow step is your mom making the cookies.
Hurry up, girl.
Because as soon as the cookies get
Crank that up.
produced, what happens to the cookies?
They're gone.
They get consumed, okay?
Yes.
So they're there, but you better get them fast or otherwise they're going to get consumed. So this NO3 is what we call an intermediate. We produce it, it's there, but then it gets consumed. So if you look at this, it appears blue. I throw it up in the air and it lands and it's purple. Okay, throw it back up.
It's
Oh,
purple.
hold on.
Oh,
That goes back to blue.
that was good. That was a fun cue.
Okay, so if you look at this in terms of how this comes apart, okay, come on. Work with me here. Well, I'm trying, there we go, kind of got it apart. Okay, there we go, okay. So, as this appears like this would be analogous to the NO3. So, you have to look very, very quickly to observe it in this state. Because if you drop it, it doesn't appear anymore. So up there at the top, like in slow motion, if you could freeze frame it, you would see it appear in this transition state. That's what's happening with the NO3. You produce it, but then it gets consumed. Now, what we're going to do is we're going to add these reactions together, just like you do half reactions. So if I add these together, my NO3s are going to cancel out, which is cool. That's what I want to have happen. So the rule with intermediates is that you can have them, but they can't appear in the overall reaction. So I can use them as part of the wizard story, but I can't keep them in for the final production of the story. It's like, hey, the wizard's doing this, but not part of the story. So we can have this, but then it's got to disappear. So then if you look at what happens, then I've got an NO2 over here and an NO2 over there. Those cancel out. So what I have left with is NO2 plus CO yielding NO plus CO2. So if I do this, if I say, okay, here's the proposed mechanism. I have a slow step that's dependent upon the concentration of NO2. Cool. That's what allows it to fit with my overall rate law. That's one of the key components. I propose that I form an intermediate, but then it gets consumed rapidly. That's cool. That works as well. And then when I add them all together, I get the reaction that I explain overall. So the only time you have to do this is if you look at a reaction and the rate doesn't match with what you would propose if it was just a single step reaction. Okay? So this is what's going to happen on the lab next week. You're going to do a lab with iodine. This is what I'm talking about. You're going to have hydronium ions, which in the overall reaction, you're going to make hydronium ions. That's going to be an overall product. But you'll see that the reaction is actually dependent upon the concentration of the hydronium ions. So what that means is that we have to have some wizardry happening behind the curtain, and we have a step that somewhere along the way, that reaction is dependent upon the hydronium ions. So that means we have to have some weird sub-step that's a slow step that's dependent upon the hydronium ions. Kind of got the idea. Got it? Good. Great. Okay. Now. Oh, it's not bad.
There's always
We're okay.
You did your fun.
Now we're going to make one a little bit more complicated.
Okay.
Not bad, just a little bit.
one. It's fine. Don't even care.
Rude.
No, and I've had too long.
The assignment isn't very long, if that helps.
She says it yesterday.
No, that was yesterday's. This isn't, this isn't.
No, it's second. Because like you grafted it or whatever, but the equation that you have isn't.
You're gonna get 3 of those.
Oh.
Yay.
I say just graft it.
Where at?
You did graft it. You gotta figure out why it's
It's a
secondary.
right.
Oh.
Where's the R coming from?
The reaction up top.
Actually, something might be better.
Don't care.
Oh, no.
Oh, they are numbered. They're Roman I just saw 2 eyes and I went, yes.
Ah, yes. Right.
Right.
Once I told everybody watch this situation, he was just giggling.
Oh, I feel bad for people who have to watch these.
No, they're
I
fine.
completely tuned you out.
I would like to formally apologize for my great commentary.
Okay, well, in my defense,
What did
that
you
looks
say?
like the little animals that roll into a ball.
It's fair.
The real one.
Yeah. What about it?
Or can you just sit there and throw the thing in the air repeatedly
Why
for
would you
me?
not just put it in the
I
natural
could,
water?
but that's gonna get pretty boring.
I don't think so.
I think it is.
Here's K.
I'll be entertained.
Ollie's.
I'm more about outside the pool.
Well, I said, no, I said
That's
this.
the natural log of your initial cancels out if you.
No, I was saying that like, it doesn't take a lot to change.
So you just did that.
Ow?
Well, you were saying that like, you could throw that up in the
It's-
air for many hours.
Did you see it?
That looks right. That's in the book.
He was like, I think that'd get boring. I'm saying that was, you don't need a lot.
I was like the second part of the.
Okay, so here we go. So here's this hypothetical reaction, 2A plus 2B yields C plus D. So again, if this, and here's what the big idea, is that if this was an elementary reaction, and it had just happened in one step, based upon this, the rate law would be R equals K times the concentration of A squared times the concentration of B squared. If this was an elementary step, that's what it would be. But it's not. Yes?
Did you forget a plus B in the third one?
No, it's okay. Just go with it.
Okay.
It'll work. No, there does need to be a B there. You're right, because there's 2 B's.
Yeah.
I had marked it out to show that it cancels out. That's what. Oh, no, the whole thing is wrong. Hold on. It only needs 1 B. That's why there isn't a B in there.
What?
There only needs to be 1 B.
They're speaking in the language of God.
Okay, so
They're using simple words.
as a potential mechanism, and there's some certain things that are important about how this is written. First off, what are you going to call X? An intermediate, right? Because we're going to make it, but then we're going to consume it, okay? Now, there's another important thing that's going to happen here. Notice that on this fast step here, you have a set of double arrows. So what that means is that this can reach an equilibrium point where you combine them to produce X, but then that it's just like what we did with the water. You know, hey, you can get that water going back and forth, but eventually that water reaches a point of equilibrium. That's what's going to happen with X. So here's why this will work. If I can hold on to my pencil. So on your slow step, first off, what's nice about this is that I can produce X, but X is going to drop out because it's an intermediate. I got a set of arrows there which allow this to form an equilibrium point. And as soon as I make Y, Y is going to get consumed. So this reaction actually has how many different intermediates? 2. Now, here's where you run into like the physical realities of this. You can produce this as a mechanism, and then you actually run the reaction, and it's like, well, we never actually see Y being produced. The reason that we never see Y actually in there, we can propose it as part of a mechanism, but it's just like the chocolate chip cookies, okay? Mom makes the chocolate chip cookies, boom, they get consumed. So your neighbor walks in and goes, man, it smells like chocolate chip cookies. There's no chocolate chip cookies. Evidence is there, but there's no chocolate chip cookies. Well, it's like, they were produced, they just got consumed. Okay?
They went to a good place.
They went to a very good place. Now, so here's what's going to happen. If this was the slow step, okay? If this was the slow step, you would say, oh, based upon this, the rate should be based upon K times the concentration of X times the concentration of B. But we can't have this. Why can't we have this?
There's no concentration.
I can't have X because of the fact that it's an intermediate. So I got to get rid of that. Now, here's where this becomes important. Because of the fact that you have this first line where you have arrows going back and forth, that can establish its own equilibrium. So because of that, I'm going to come down here and go, oh, that means that the rate going forward can equal the rate going in reverse, because I got that set of double arrows. Though at some point these two rates are going to balance out. Cool. So I can write the forward reaction as K times A squared, and I can rewrite the reverse one as K times X. Cool. Now, math to the rescue. So if these are equal, what can I do?
Substitute.
I can substitute that in for, ooh, okay? So I can substitute that in there and go, oh, that's going to be K times Ka squared times the concentration of B. Now, don't look at this and go, oh, you get K squared. They're just K's. Don't worry about it. Okay, it's just a generic K. So I can rewrite this as just K times concentration of A squared times the concentration of B. Now, the beauty of this is that it matches with what we said in terms of the overall. Okay? So, but then you're going, well, if that matches, what's the point? So why this would be important is that when you would run that reaction, because of the fact that you have a slow step where you could detect the presence of X, because this is the slow step. So you run the reaction and you go, I know X isn't part of the overall reaction, but when we run the reaction, there's a phase of this reaction where we see the value of X. We see the essence of that. Maybe there's a cup of walnuts on the counter. It's like, oh, walnuts are here. Somebody's making chocolate chip cookies. If you don't like walnuts in your cookies, you're a communist. I'm just saying. It's like, I don't like walnuts in my cookie. Communist.
You're just afraid.
I'm just saying.
You're afraid of eating.
Although I did get turned on to, have you ever had the Nestle's cookie dough like in the tub? Have you ever eaten that just straight up? Oh my God, that's like crack cocaine.
Oh, way worse. Way worse than crack cocaine.
I mean, I'm serious. Like, I hate to say it, but I was like that. I only got that experience like a year ago. Like, I have spent the vast majority of my life
He's
without
had
that.
breakfast every morning.
So, like, literally now when I walk back by that in the grocery store, like, I have to do this.
The best are like the ones that are alredy cut into like the little squares.
I say I've never gone down the little square road.
Oh, they're
Oh,
so
good.
good.
No,
Those
see,
are-
I
those are
think
words.
that's gonna be
They're
more like crack
they're
cocaine, it's like,
Yeah,
hey,
because it's like, you're like, oh,
Slide
it's
that.
not like blood.
Okay, the hard part about little squares
Is
is
what?
that you can convince yourself to eat one.
Yes,
Once you eat
but
one,
you
you're
can never
not
stop.
You're never just
I
eating
don't
one.
feel bad.
You don't.
Okay, all right, that's it, I'm done.
Yay.
So stop that, let me hand out the assignment, and then